We're going to talk about a very important application of the cross product, which is torque. So in physics, torque is a measure of rotational tendency. It's like the rotational equivalent of linear force. The torque is a vector, although the word torque itself is often colloquially used just to indicate the magnitude of the torque vector, so just how large the torque is. But technically, the torque is itself a vector. The direction of that vector indicates the axis of rotation, so you're always rotating about an axis. And that is given according to the right-hand rule, and I'll go over that in just a second. The magnitude of the torque vector is usually what is stated as the torque. Now, the SI units for torque are the Newton meter, which is dimensionally is equivalent to the joule, but we don't use the joule because, and I'm not a physicist, so I'm not really properly equipped to explain this the best way, but the joule is a unit of work or energy, and we're not really measuring work or energy in this case, so we just leave it as Newton meter. But dimensionally, it's the same unit, but you want to report it as Newton meter, not as a joule. So let's look at a wrench here. So let's say that we're tightening a wrench. So bring this down here. So the setup is that we have two vectors. So we're measuring from, say, so really it's the very center of where we're rotating about. So here it would be right here. But the one vector is going to be what we'll call a position vector. Let's say that I'm applying the force all the way out here at the center here. And let's say that this position vector I'll call R. Okay, so this position vector is saying what's the vector from the center, so from the axis of rotation out to where I'm applying the force. So this is a position vector. Then I'm also going to be applying an actual force. So let's say that I'm applying it at a certain angle here. So let's say I'm applying it this direction. Call this F. So this is the force applied. So the torque vector is denoted by tau. So it's tau with an arrow above it, or if you're reading it in a book, it's probably going to be tau in boldface. So this is defined to be the cross product of the position vector with the force vector. So let's think about why this is a reasonable definition. So if we draw, let me just kind of draw a horizontal through these two. Okay. So think of this horizontal going through here. So really, this would be, again, R here. Now, what I can do is break down this F into its two components, so like we did with projections. And there's one piece of it that's going to be going all the way over to here. And then there's the orthogonal piece that is going to be going down to the tip. And the point here is that only the red vector here is really contributing to any rotation, right? Because it's the part of the force vector that's actually perpendicular to the position vector. So if we call this angle here, I'm going to call this angle theta. So if we call this angle theta, then it's pretty clear that the magnitude of this piece here, so the red vector, is going to be the magnitude of F times the sine of theta. That's just from trigonometry. So from physics, we know that the torque is going to be directly proportional to the distance from the axis of rotation, directly proportional to the magnitude of the force. And so what it should be is the product of the magnitude of the torque should be the product of the magnitude of R and then this magnitude of F times sine theta. and we're going to call this just tau without the vector, so that the magnitude of the torque vector is just going to be tau. So we see that that would be r times f times sine theta. And remember, that is exactly the formula for the magnitude of the cross product. The magnitude of the cross product was the product of the magnitudes of the two vectors times the sine of the angle between them. So that makes sense. So the only other thing to really keep track of here is the right-hand rule. So where is this pointing? Okay, so let's think about this. Let's say we were tightening. Well, let's start with, let's say that we were loosening the wrench. So lefty-loosey. So if we're loosening it, then R is going this way. Now, again, lefty-loosey. So you're going to be applying the force up this way. So what's the R cross F going to be here? This would be like R and then F if we were to put them with the same initial point. In that case, the right-hand rule would say that that the torque vector should be pointing towards, out of the plane. So it should be pointing towards you. So the torque vector points towards you. So if you're sitting, if you're looking at a wrench and you're loosening it by going, in this case, so counterclockwise. Counterclockwise. If you're loosening it this way, then the right-hand rule would say that the torque vector should be pointing out of the page towards you, should be pointing at you. Okay. Now, what if we're tightening the wrench? Righty-tighty, right? So now we've got the position vector. Now we're going to be tightening it by going this way. So just the opposite. So we've got R, but now the force is getting applied downward. In other words, we're going, instead of counterclockwise, we're going clockwise, which means that the torque vector should be pointing away from you. So it should be pointing out of the page away from you. Okay, so that is the torque vector. And again, colloquially, when people talk about the torque, if they say the torque is this many Newton meters, they're talking about the magnitude of the torque vector. The torque is the actual vector that indicates the axis of rotation and whether you're tightening or loosening. So here I've drawn the torque vectors. You kind of have to imagine this in 3 dimensions. So here, the blue vector, that's the case where the torque, where you're loosening the wrench, the torque is pointing towards you. And then the red is if you're tightening the wrench. In that case, the torque vector is pointing away from you. All right, so here's the example. A force of 10 newtons is applied to the end of a wrench of length 15 centimeters in order to loosen a nut on a bolt. Okay, so the wrench is angled 30 degrees above the horizontal. So you can see here I've drawn the position vector R and the 30 degrees above the horizontal. And the force is applied at 80 degrees above the horizontal. I got mixed up the problem I was copying from. I put 20 degrees below. So it's 80 degrees above the horizontal. So you can see here now, at the tip of the position vector, we're applying this force at 80 degrees above the horizontal. And you can see that's going to loosen the nut. Find the magnitude of the torque vector and describe its direction. Give your answer to the nearest hundredth of a Newton meter. So let's start with the magnitude. So the magnitude is going to be the product of these two. So product of the magnitudes times the sine of the angle between them. Okay, so a couple things to be careful of here. The magnitude of R, if we want our units to be in Newton meters, we have to realize that 15 centimeters is 0.15 meters. So 0.15 meters times the force, Now the force was 10 newtons. Okay. Times the sine of theta. Now we have to figure out what theta is. So from the picture, now remember that the angle here is the angle between R and F. And so what you have to do here is realize that the angle is really given here. And that angle is going to be 50 degrees because we have the same 30 degrees here. So 30 plus 50 is 80. So we're really taking the sine of 50 degrees. So sine of 50 degrees. So this is going to be 1.5 times sine of 50 degrees Newton meters. So let's see what that makes. So that is about 1.15 Newton meters. Leave a dot there. And then we need to describe the direction of the torque vector. So in this case, since we're loosening the wrench, the torque vector is pointing at us, towards us. Okay, so that is torque. In the next section, the next couple sections, we're going to be talking about some things that are not really so much related to vectors, but they're things with three-dimensional space. We're going to be talking about equations of lines and planes, and then going over some of the quadric surfaces.